Okay, so in the last class we were discussing about like various computer vision related tasks which can be which can be useful for remote sensing. So like we had already discussed about these tasks of object detection and then of image segmentation. So in case of image segmentation, like in case of object detection, as we saw that we are given an image and we are looking for certain objects in an image, and then we have to search that image at multiple scales and multiple locations, so which is done by this framework of YOLO, or you only look once. So like it's a neural network consisting, like as you can see, this is the architecture consisting mostly of convolutional layers. And so like this thing, it works at or it multiple I mean multiple boxes in the region of this the image, and in each of these boxes it tries to assign some kind of a probability score whether that particular box is associated with the target object or not. And accordingly, once like all regions of the image, they have got some probability distribution on the different classes, I mean the different types of objects that we are looking for. Then after that, there is a bounding box prediction layer which collects those probabilities and proposes the bounding boxes, like say for example that this region contains one object, these regions contain another object, and so on. And similarly, another very important task is image segmentation. So like we call it semantic segmentation, because like the segmentation is done based on semantics of the image, or rather like say the objects in the image. So like this, so as you can see here in this image, there is a like a road. So the end, so all pixels which are associated with the road, they are given they are given one pixel intensity. Similarly, all the images that are related to these cars, they are given another value of the pixel intensity, and so on. So this kind of thing is done by first like coarsening the image progressively, as is done by successive layers of convolution and pooling. And then after that, like once we have coarsened the image to a very like a small and coarse level, after that we try to upsample it back to the original resolution. However, while doing so, we make sure that the pixel values that is we the original pixel values are not restored, but rather the pixel values are like this, that is in whenever any two pixels in the original image, they belong to the same region, they are assigned the same pixel value in the or equal pixel value in the output image. So and to ensure that this happens, like this kind of a network also uses skip connections from that is like these kinds of connections, these are called skip connections. That is they like here there is a connection from these layers to these layers, bypassing the intermediate layers. So again, from here to here, they like we have a skip connection bypassing the intermediate layer, and so on. So like these kind of skip connections, they help us to maintain a symmetry between the downsampling phase, I mean the upsampling and the downsampling phases. And that is, and like it helps us to make sure that each of the images obtained like at an intermediate step, there is a correspondence between the image that was like obtained at the same resolution while we were downsampling the image, right? And this is so this is done using the standard like this kind of thing. This kind of a structure is usually called an U-net. So as you can see, this is in the shape of an U. That is, we first go down, and then that is by doing the process of downsampling, and then we come up by the process of upsampling. So now today so these are the basics of image processing. So now our computer vision. So now we will see some use cases, and we will also make a quick survey of different research papers which utilize these ideas. So for this purpose, first let us consider the task of object detection in case of satellite imagery. So satellite image is so like one very common class of applications of object detection in satellite imagery is that when we are basically we have got satellite imagery which may be either in the visible range, I mean the RGB kind of image, or they can be like say SAR images, so synthetic aperture radar images. So these kinds of images are also often obtained from the satellites. So different formats of images, they like or hyperspectral images. That is, the different images are taken at the different wavelengths, and like they have different kinds of images have different uh, properties. So anyway, the central idea is that once we have a satellite image, we need to locate certain kinds of various kinds of objects in them. So like for example, like this is like in this image, as you can see, we are trying to look, there are lots of boats or ships parked in a something like a harbor, and the task is to like identify the different boats, and I mean, or maybe count how many boats are there. Similarly, here we can see a parking lot, and we want to count how many cars are parked. So like basically here the target is something like a ship detection in an image, or car detection in an image, or here it might be aeroplane detection in an image. So the challenge is that like we first of all we have to, like we may have very large number of images like this, but most of them will not be labeled. That is, it is very difficult to actually sit and label all these images. It is not enough to only label the presence of the objects which we are interested in, but also we have to provide the bounding boxes around each of the images. And then only once after doing the bounding box annotation, then only we can provide these as an input for training a neural network. And then the neural on a test image, like that is basically the neural network will be able to learn a model for that particular object whichever we are interested in, be it car or plane or ship. And then only on the test image we will be able to do it. So obtaining the labeled examples, I mean, that itself is a huge challenge in this case. So people have to utilize the ideas of semi-supervised and learning. So in case of semi-supervised learning, what happens is that we are provided with with a small number of labeled images and a large number of unlabeled images. So then we have to search for similarities between the labeled images and unlabeled images, and then like kind of auto label the unlabeled images, and then use those unlabeled images for the purpose of training the models. So typically, like when we are looking for or we are trying to search for a class of objects, let us say in this case plane, then we must learn, that is, we must look for two kinds of labels, or two kinds of images. One is positive examples, other is negative examples. So these are some of the positive examples, some labeled positive example where a person has actually sat and put a bounding box around these planes. And then there are also some negative examples. So these are like, as you can see, as or as may be visible, like these are some random landforms, or maybe either some forests or some water or some cities. So these are basically the negative images. So that is when we are training to detect the aeroplanes, we have to like give the model some positive examples that this is what an aeroplane look like, and we also have to train it with negative examples that this is what the aeroplane does not look like. Then only it will learn to differentiate between the things. So So like only again, as I said, in both cases, for both positive and negative examples, only a small number of labeled images are available. A large number of unlabeled images are available, of course. So we have to find a way to utilize the unlabeled images to like strengthen the classifier. And once that that binary classifier is trained, then we can like run it on the test image and like try to locate all the aeroplanes that are present in the test image. Similarly, we can do it for other object classes also, say ships or cars and so on. So this is like one example of object detection in images. Similarly, we like another very important that is a task of image segmentation also comes very frequently in case of these satellite when we are dealing with satellite imagery. So especially for the task of say land use land cover mapping. So that is land use land cover means like which like so we have a satellite imagery like this, and then from that we want to understand which like I mean how much which parts of the world world surface are being used for say agricultural purposes, how much of it is built up areas, or I mean to say has buildings or similar structures, or how many or how much regions, or if we are focusing purely on a city, then how much region is, let's say, parks and gardens, how much region is lake, which regions are the roads and things like that. So this is the so-called LULC problem, the LULC mapping problem. So every single like we have to do the segmentation of the image at right up to pixel level. So all the pixels which cover some, let us say, one kind of land use, they will get like they will be considered as one cluster of pixels having one color, or then another class, let us say the grasslands, like we'll have to identify all the pixels which are present, like which may be associated with grassland. So and we have, and like those will be considered another cluster, and so on. So, so in general, this is quite a difficult task because in the like when we are looking at a satellite image like this, in general, only the top is visible, and so that is like if we that is just from based on the top, we have to like identify or like which is or which pixel is what. So. So again, for this purpose, deep learning is used. So we actually have to provide a like a trained I mean an annotated data set where we have like like at where pixel level annotations are available, which is of course very difficult. So and also very expensive. And then however, one saving grace that is there is the property of spatial coherence of the pixels. That is like any structure is unlikely to be bounded by a or restricted to a single pixel. If this pixel belongs to class A, most likely its surrounding pixels will also belong to class B. So like we need to learn some kind of a relation. So at every pixel we have some intensity, so like some kind of intensity. Like in an RGB images, we have R, G, and B values. That is in the different color channel values at every pixel. If instead of RGB images, if some other kind of image is taken, then also the different channels will have different values. So basically we have to we have to learn a mapping from that is from like every each pixel, like at every pixel, given its the pixel values along the different channels, we have to learn to map that to an object class along with some kind of a like a probability distribution, that a pixel with such and such intensity values along the different channels belongs to say class grassland with probability 0.3, or belongs to class road with probability 0.2, and things like that. And so that is so the intensities of the pixels, that is one queue. The other queue comes from the like the surrounding pixels. That is, we know, as I said earlier, we know that the like the any of like it's unlikely that two adjacent pixels are belong to two different classes. So like we have to consider that that property of spatial coherence. So if at a for in a particular pixel, if we are not sure about its what class level it is, we can consider the surrounding pixels and make a and be stronger about and be that is, and our belief about its class level can be strengthened. Then besides, we can also have some cues about which kinds of structures are unlikely uh, happen or appear side by side. That is, it's for example, if we are focusing on a city where there are lots of building, it is unlikely that there will be an agricultural area or a forest next to a building. So such these kinds of different I mean such kind of domain knowledge also have to be built in while predicting the labels of the images. So, but again, rarely we actually do. It is very rare that we actually sit and build this kind of or provide this kind of this kind of knowledge by actually like providing that a grassland and road are likely to appear adjacent to each other with so much probability, or a arable land and desert are likely to occur side by side with this much probability. That we do not know, but rather the we need to uh, train the neural network itself so that it can itself find or learn some kind of a relation between these, and then that learned relation can be utilized in the subsequent predictions. And it is like the task and or the operation of convolution becomes important when we are doing these kinds of things. That is, the convolution, as I said yesterday, is a task of considering the interactions of one pixel with its adjacent pixels, and for that purpose we build these kinds of convolutional filters. So the again the like earlier, before the advent of the deep learning era, the convolutional filters we used to ourselves construct and then slide that filter all over the image to see which are the responses. And then when we build those filters, we build them according to some kind of an intuition. That is, maybe we are trying to look for vertical edges or horizontal edges, or isolated points, or maybe diagonal edges or stuff like that. But in the deep learning era, we usually do not ourselves manually construct the filters by hand, but let the network itself figure out what kind of filters will best be suitable. So maybe it will it will be able to find out a suitable filter which is capable of detecting buildings, another filter which will be capable of detecting the say the road structures and things like that. And we actually also have apart from use land cover, we also have some very specialized applications, like say the road network extraction. That is, given an image like this, we identify all the roads and actually extract the road network in this city. With all, also here, as you can see, these whites, these indicates the different roads. All the roads are indicated in white, and with all the road junctions are also clearly indicated. So identification of a particular type of landform, be it the road network, or be the, let us say, the forested region identification, or the water body identification. These are kinds of things are they are all based on this segmentation of images with the help of deep learning. Okay. And so, as I said earlier, this kind of thing, for doing this purpose, this kind of tasks, we usually use UNet type of uh, networks. that is different researchers have used different versions of this UNet for the purpose of uh, image segmentation, but most of them utilize the idea of skip connections at some level or the other. And so like typically it looks like this, that is the input image is something like a satellite map, and then which is passed through a series of convolutions and poolings, and followed by again a set of another set of convolution and pooling, etc., and until we reach the what is known as the bottleneck layer. Right, the bottleneck layer is like the smallest form of the image, or the condensed representation of the image. And as you can see, like these are like at every stage there are multiple, you can see these copy like structures. So each of these are like we can say along different channels the image is being convolved. So like for every you can say that we have a separate convolutional filter for each of those channels, and those convolutional filters at the same level, they are they are looking for different kinds of stuff in the image, different kinds of structures in the image. Those structures, they may or may not be interpretable to the human beings. That is, they can be something like on we have a building filter in one image, we have a say road filter in another image, and things like that. But most likely that will not happen. Rather, it will like the network will find some structure which it finds suitable, maybe for buildings or maybe for a subset of the different classes and stuff like that. And so most likely will not be able to interpret the classes, I mean the interpret the filters. And then like once we have got a set of these copies of the different channels at one layer, then after that we will do the pooling operation, which will shorten like make the images reduced in size or condense the images. Then again on the condensed images, I will again do the same set of convolution operations at like along the different channels. We may create more channels in this case. And then after that, we will again do the pooling, and then again create a smaller, more condensed representation, and so on. So it is a challenge for researchers to actually investigate all these filters and all these feature maps at the different levels, or the different layers, and try to interpret what those things actually indicate, or what they actually stand for, what is represented. Because this process of building filters, etc., this is not fixed by human beings. The neural network itself learns what can be a good filter value for the purpose of classification. So if any of you want to do a project on this purpose, I think that will be a good project topic, to actually build some kind of a satellite image segmentation network for the purpose of say LULC mapping and so on, and then try to visualize what is learned by the different hidden layers. So like a large like quite a few research papers have appeared in it. So the initial structure was the UNet, and then after that, based on that, another thing came up called SegNet, which is also based on this idea of uh, these skip connections. And like here the indices are like themselves propagate these indices uh, are propagated, that is by indices, by pooling indices means like which set of pixels are being pulled together and things like that. And like when we are that is when we do the process of pooling, we are basically making we are throwing away some important information, I mean some information. That is, we have like we are focusing on a particular set of pixels. We preserve only the larger value and throw away the smallest values. But we usually do not remember exactly which of the pixels contain that largest values and which contain the smallest values, smaller values. We just usually maintain one pixel which contains that large value, but the other values are simply forgotten. But here what they are trying to do is they are actually trying to remember out of the that is when I am throwing away the smaller pixels and keeping on the smaller pixel values and keeping only the larger pixel values, they also remember which pixel actually contained the that larger value, so that when they reconstruct it, they utilize that information for the reconstruction purpose, and that makes the reconstruction look more coherent. So so there are like various small properties can be tweaked around in the different networks, and so that's what they do. Another important topic that arises in this context is that of domain adaptation. So we know that these satellite imagery is not easy to obtain in all parts of the world. I mean, there might be some regions on which there is a denser availability of satellites, or maybe the presence of satellites are can be apart from satellites. There can be also like other sources of information, like say drones uh, or radar images or things like that, or maybe even ground level data is available. So there might be some cities in which very detailed survey has been carried out. That is, it is also known that which region of the city contains what and things like that. But then there are maybe also the cities in poorer countries where such a detailed survey has not been done, or there may be some forested regions, etc., where maybe where there is no one to fly a drone around that region and get the greater details and so on. So in that case, like the detailed information which we can get in some regions, such detailed information is not obtained from the other regions. So if we, but as I said earlier, to do the thing like this kind of a object detection or segmentation, we need a very detailed labeled imagery. That is, we need pixel level details of which pixel contains which object and stuff like that. But in those regions where such detailed information is not available, then it is very difficult to get the pixel based information like that. So then what to do? The answer is to go for domain adaptation. That is, we train a neural network specifically for those regions where we have the like detailed all the like the detailed pixel level data is available. We like train the that neural network. We utilize the or we make the class predictions for the different regions, etc., and accordingly we can calculate the loss function. And then once that that image has been I mean, once that neural network has been trained, it can be utilized in a different domain, or maybe in a data poor region with some minor modifications of that thing. So maybe that is, since the less data is available, so we do not have enough like it is not possible to train a fresh neural network for that, or that is because a neural network will have millions of parameters. So if we do not have enough input data, we cannot meaningfully train all those millions of parameters. So what we will do is we will import most of the parameters from an already trained image, and only do like a simple calibration of maybe one layer, or maybe the last two layers, and estimate their edge weights, keeping the other edge weights incomplete. I mean, undisturbed. And so that so like typically like we do this kind, that is, we actually do the domain adaptation. Like while doing the domain adaptation, we learn this kind of a domain adaptation loss along with a classification loss. So like which indicates like in the different like maybe in the domain where we have trained the image, maybe the different class levels have one particular distribution. In the other domain where we will be deploying it, maybe the class levels have a different distribution. So there will be, so we have to account for the difference of this class level distribution. So that is taken care of by using the domain adaptation loss. And so there are of course specialized data sets which on which this purpose this particular task of domain adaptation can be tested. And so it's like we have for the so because so that we can evaluate it, people do is for the same region they identify different like different kinds of things, maybe at different resolutions or maybe different orientations also. So that is like they like in one data set like we have agricultural lands, and in another data set taken from one particular angle, in another data set we have something called farmlands which is collected in a like maybe the same things, but the pictures are taken in a different way, maybe in a different orientation. Similarly, there might be some region, some in one data set there is like they focus on airplanes, in another one they focus on airports. Like at that is here the focus is on individual planes, here the focus is on the large scale appearance of the airport, and this such stuff like that. So it is necessary to calibrate the different class levels in one case with the different class levels in the other case. And so for that calibration there is like a loss function is used to do this so that this calibration can be done meaningfully. So that is like known as the domain adaptation loss. And so accordingly this is done. So this deep domain adaptation, this is also a very important uh, idea behind, or I mean it's a very important task in the this remote sensing, because as I said, there are some data rich regions of the world where detailed labels, pixel level labels are available, and there are large parts of the world which are data poor. That is, we may have satellite imagery, but they are unlabeled. So then, how do we train a neural network in a data rich region and then deploy it for a data poor region? So again, this is also a topic on which you are encouraged to, that is, some of you are encouraged to do a project. Okay, now what we will do is we will do a summary of some research papers. So let us we'll quickly go through maybe 5 or 6 research papers like this, not the great details, but only the relevant parts. So let us look at the first paper, which is on skyscapes. So let us see the paper. Let me share it. Let's read the abstract first. So understanding the complex urban infrastructure with centimeter level accuracy is essential for many applications, from autonomous driving to mapping, infrastructure monitoring, and urban management. So see, that is the accuracy they want is at centimeter level. That is, they want if two things are separate from each other at a like by like there is 1 centimeter gap between two things, still those things have to be identified individually. That's what they ideally want. I mean, they may not be able to achieve it, but that's the kind of it is that level of detail at which most modern applications require I mean the requirements is at that level of detailing. So aerial images provide valuable information over a large area instantaneously. Nevertheless, no current dataset captures the complexity of aerial scenes at the level of granularity required by real-world applications. To address this, we introduce Skyscapes, an aerial image dataset with highly accurate, fine-grained annotations for pixel level semantic labeling. So nowadays we can get very high resolution satellite imagery, and like the higher the resolution, the more like the finer is one pixel. So like maybe even 10-15 years ago, like one pixel could usually stand for maybe 100 kilometers or so. Then another, maybe another 7 6 7 years earlier, one we could have like one pixel could cover 25 kilometers. And now it's possible to get one such images where one pixel is like is a matter of covers only a matter of, say, maybe a few meters. So and they are aspiring for centimeters also. That is, ideally they would want each pixel to stand for a few centimeters. So that is to say, they like each pixel should become like as or should focus on as minute details as possible. If a pixel represents say 100 kilometers, that means the internal differences will all be blurred out, because a pixel can have only one value. So it's like for 100 kilo, for a region of 100 kilometer by 100 kilometer, you will have only one value. But actually for any practical thing, there will be a lot of difference of a lot of variation within that 100 by 100 kilometers. So that information will all be lost. So I want the pixels to be as small as possible, and according to their demand, I want it up to centimeters scale. So now, to address this, we introduce Skyscapes, an aerial image dataset with highly accurate fine-grained annotations for pixel level semantic labeling. Skyscapes provides annotations for 31 semantic categories ranging from large structures such as buildings, roads, and vegetations to fine details such as 12 subcategories of lane markings. Okay, so like the different labels of the which they attach to the different pixels, that is again hierarchical. Like there can be categories, large categories like buildings, roads, and vegetations, and then there under them there can be sub categories like say among buildings there can be like maybe high rise buildings or maybe small houses. These can be subcategories. Then roads can be like wide roads or highways or pathways or moderate or medium city roads. So each of these like there can be multiple labels associated with each pixel at multiple levels of detailing. We have defined two main tasks on this dataset: dense semantic segmentation and multi-class lane marking prediction. We carry out extensive experiments to evaluate state-of-the-art segmentation methods on skyscapes. So, image segmentation methods are already available. So, on the dataset which they have got, will compare multiple image segmentations approaches and see how they compare. Existing methods struggle to deal with the wide range of classes, object sizes, scales, and fine details present. We therefore propose a novel multitask model which incorporates semantic edge detection and is better tuned for feature extraction from a wide range of scales. This model achieves notable improvements over the baselines in region outlines and level of detail on both tasks. Okay, so that is what the abstract is